To a quick video tutorial on exponential functions. This particular video is going to look at the graphs of exponential functions, and we're going to do this in order to determine their properties. The first example I want to look at is a graph of a function called f at x equals 2 to the power of x. And what we're going to do is sketch this thing. We're going to do that by generating a table of values. So remember, with a table of values, you can sort of just arbitrarily pick x values, and you can take these x values and put them in for x in your function. And when you do that, what you get is some sort of output. Right? You take an x, you put it in, and you're going to get some y values out. And I represent those y values as f at x in this y column here. All right, so what this means is if I take some number and I sub it into my function, that's going to tell me that I'm going to do 2 to the power of that number, which another way of writing that would be 2 times 2 times 2 times however many 2's I happen to have for the x value I've subbed in. So an example of that would be if I take an x value of 1 and I substitute it into my function, I'd have 2 to the power of 1, which we know is 2. Okay, and if I continue down my table, if I sub in 2, I've got 2 to the power of 2, which is also known as 2 times 2, which would be 4, and I can continue. 2 to the power of 3 would be 8, and so on and so on and so on. Okay, so that's great. I've got some x values, but it would be really nice if I was able to go backwards and kind of sub in some other values that would help me paint a better picture of what's happening on this graph. So if I sub in 0, you may or may not know this at this point, 2 to the power of 0 is 1. And if I go even further, negative 1, 2 to the power of negative 1 is 1 over 2, and so on and so on. I can continue in this way. If you're not really sure where this is coming from, maybe from here on, I do have some videos posted on zero exponents and negative exponents that you might want to check out. That'll sort of contextualize what's happening here a little bit. So I'd encourage you to watch those videos and then pop back over and check this one out. So what I have here is a table of values. I'm able to graph this, and what I've done is just quickly graph this on a graphing calculator. But you can see here, each of these x values corresponds to a y value, and I've plotted that on my graph. All right, so when I sub in 0, I get 1. When I sub in 1, I get 2. If I sub in 2, I get 4, and so on and so on. And that continues in this direction as well. And you can see here, if I sub in bigger negative values, I'm getting smaller and smaller numbers. So I've got a fraction with a denominator that's getting bigger and bigger, which means this number is getting closer and closer to 0. But you can imagine if I'd sub in a number like negative 100, for instance, for your x value, you would get 2 to the power of negative 100. Which would just be 1 over 2 to the power of 100. That's a really, really, really small number. So it's getting close to 0, but it's not quite 0. And that's what we call an asymptote. I'm going to talk about that a little later in this video. Okay, but if you take a look at this pattern here, as I go up my table of my y values, I'm essentially multiplying by 2 every time. So if you take, for example, this y value, if I multiply that by 2, I get the next y value. If I multiply 2 by 2, I get the next y value, and so on and so on and so on. And this shouldn't really be a surprise, because the reason I'm getting this is if you look at the function, I have a base of 2, right? Because I took 2 and I multiplied by itself, however the number of times that I picked in my x column. Okay, so that's where this graph comes from. It's just plotting my x and y values. This question here says explain how you know this relation is a function. If you think back to earlier on in your study of functions, you learned about something called the vertical line test. If I pass this vertical line through the function, you can see there is never a point on this vertical line where there are 2 points on my graph. Right? And you can see these red points as I pass through my vertical line through the function. There's only ever 1 point on that line. Okay, and that's one of those properties of functions that I've talked about, where it has to pass what's called the vertical line test. All right, so here's a couple follow-up questions. We've talked about domain and range in these video lessons. Domain being the set of all x values, range being the set of all y values. Talking about the domain and range for this function, if you look at the graph, you can see here, I can write out the domain as I can pretty much sub in any x value, and I did sub in a few. I even subbed in negative x values. I could sub in fractional x values. I can really pick any x value I want. And when I do sub in an x value, I should get a y value. So you can see here, if I sub in 1.5, I'm going to get some number in here. If I sub in 1.9, I've got a y value here. Okay, so the way I write this is I say that x can be what's called an element of the real number system. Okay, so XER is how that's written. Okay, talking about the range, this is a little different. The range refers to the possible y values. Now, I can get any possible y value. You can see here if I sub in 3, I'm going to get between 7 and 8. If I sub in 3.5, I'm going to get another number between 7 and 8, and so on and so on. I'm always able to get any possible y value. However, like I said, you're never going to be able to get 0, right? There's never a number that I could sub in for x where I raise 2 to some power to get 0. That's not possible. That would break math. Okay, so it is possible for me to get any y value. Okay, so I'm going to say my range is any possible y value such that, that's just a vertical line, my y values have to be greater than 0. And I can't say greater than or equal to 0 because I'm never going to be able to reach 0. And I just showed you why that is using my table of values. Okay, talking about the x and y intercepts, remember to get y-intercepts, you simply set x equal to 0. Okay, so that's what I'm doing here. If I take x and I plug it in for x in my function, if I sub in 0, I've got 2 to the power of 0. This was actually one of my values on my table of values on the last slide here. I subbed in 0 and I got 1, and that is my y-intercept. When I set x equals 0, I have what's called a y-intercept, and you can see here on a graph 0, 1 would be my y-intercept. This is kind of a special point because for all exponential functions that are not transformed, so anything that's just a base to the power of x, you're going to see this point as a y-intercept, 0, 1. There should not be an x-intercept, and the reason for that is directly related to what we were talking about with the range. We can't actually hit the y-axis because that's one of the properties of exponential functions. This is what's called an asymptote. So part E says, write out the equation of the horizontal asymptote. Horizontal asymptote is essentially a horizontal line that you can never touch, right? And we've just talked about where that would be. I can never touch this dotted line here. I can't get a y value of 0 because there is no x value that I can sub in for x to get 0. Okay, so it's not possible for me to cross that line. It's definitely not possible for me to get any negative y values. So I'm going to say the equation of my horizontal asymptote is the horizontal line y equals 0. Okay, just another quick little example here, just kind of showcasing the difference between 2 to the power of x and 1/2 to the power of x. So same question, what would this look like? Well, if I pick different values of x, what this tells me is that I'm going to multiply 1/2 by however many times I need to for some given x value. So I'm going to pick just any given x value and try to generate a table of values similar to what I did in the last example. If I start with 1 and I sub in 1, I've got 1/2 to the power of 1, which we know is 1/2. If I sub in 2, I've got 1/2 times 1/2, which if you know how to multiply fractions, you know that that's just a quarter. All right, so I've kind of started developing my table of values here. This isn't very interesting because you can see I'm getting larger and larger fraction denominators, right? So I'm getting closer and closer to 0. It'd be more interesting if I went backwards and saw what was happening. So again, if I sub in 0, 1/2 to the power of 0, remember anything to the power of 0 is 1. So that shouldn't be a surprise. Remember that was one of those key points on the graph that I talked about. All exponential functions are going to pass through 0, 1. Okay, if I go backwards one further, if I sub in -1, I've got 1/2 to the -1. Talking about exponent laws, remember if you have a negative exponent, you can just flip your base and write it as a positive exponent. So if I took 1/2 and I flipped the numerator and the denominator and I changed the exponent to positive, it would be 2 to the power of 1, also known as 2. Okay, working backwards further, if I sub in -2, I can flip my fraction, have 2 to the power of positive 2, which would give me 4. And again, if you're a little confused on what I'm doing here, I'd recommend just checking out the exponent laws videos very quickly. Now you can see as I work down my table of values, there is a pattern, and it happens to be the opposite pattern as the last example. Okay, so if I look at this y value, the next y value should be half of that y value, and that's not a surprise, because what I did is I took 1/2 and I multiplied by itself again, right? So as I'm working down the chart, I'm multiplying by 1/2 another time, right? So I'm dividing by 2. Multiplying by 1/2 and dividing by 2 are the same operation. Now if I were to graph this, just taking these values and plotting them on a graph, you can see here I've got negative 2, 4. So if I go negative 2, 4, I've got that point. Negative 1, 2 would be right here. Of course, my special point, 0 and 1, would be right here. And you can see I'm getting a bigger denominator in my fraction as I get closer and closer to 0. Okay, and like we just discussed, this is what's called a horizontal asymptote. Remember, that's the horizontal line that the function never touches or crosses. There is no x value I can sub in which will give me 0 or a negative number. Okay, so it's definitely not possible for me to cross this line. Same equation for this horizontal asymptote, y equals 0. All right, just a follow-up question here. Compare this function to f at x equals 2 to the power of x. You can see here, just by looking at the graph, this thing starts up really high in my negative x values and kind of decreases as I increase my x values. That's the exact opposite of what I had in the previous example, where I started down very close to 0 and I increase very, very quickly as my x values get bigger. Okay, so that's one observation you can make when you're comparing these. If I've got a fraction and I'm raising it to the power of x, I've got a decreasing exponential function, whereas where I've got a whole number as a base, such as 2, I'm increasing as my x values get bigger. One similarity, like I said, all of these exponential functions that are non-transformed are going to pass through that special 0, 1 point. Okay, that's definitely an observation you're going to want to take note of. All right, so hopefully this video kind of helped you explore some of the properties of exponential functions. There'll be a series of videos kind of dealing with exponential functions, so stay tuned and check those out.